we are going to be discussing isomerism. So, all right, let's begin. What is isomerism? What is isomerism? That's right. First, the word isomerism is gotten from two Greek words. The word isomerism is gotten from two Greek words. Who can tell me? Iso and what? Mer, right? Mer. In fact, maybe it's just M-E-R. Mer. Isomerism is gotten from two Greek words, iso and mer. Iso meaning, who can tell me what iso means? From our knowledge of biology, isotonic, isotope, iso. What does iso mean? This, God bless you. The same. You remember, isotonic means the tonicity of both media rather, are the same, right? Oh, bless you. So, iso meaning same. Then, mer meaning units or fragments or parts. You understand now? Iso meaning and mer meaning unit. Now, the concept of isomerism is defined in your textbook in the context of just one type of isomerism. But we're going beyond that part today. Because in your textbook, what you'll see is isomerism is defined, that's right. Isomerism is defined as a condition, as a phenomenon on the board, as a phenomenon in which a chemical or an organic compound is a phenomenon in which an organic compound, two or more, not an organic compound, in which two or more organic compounds have the same molecular formula. They have the same what? Molecular formula, but differ in their structural formula or orientations. It's a phenomenon in which two or more organic compounds have the same molecular formula, but differ in their what? Structural formula or structural orientations. All right. So the phenomenon of isomerism is based by formulas. That's why it is based. The definition is based on formulas. So you see some things. You see some compounds that will be drawn for you, and by the time you compress it to the molecular formula, you remember we did molecular formula, right? Okay, for example, the general formula of alkanes we said was CnH2n plus 2, right? Now, I could give you this and tell you n was 3. The molecular formula, if n was 3, would be C3. The molecular formula, okay, let's say n was 4. Let's have one 4. If n was 4, is it just starting? Okay. If n was 4, the molecular formula was C4 H2 into bracket 4 plus 2. Does that make sense? C4 H what? H what? 10. Good. Now, the structural formula of this thing would be C in 4 places. 1, 2, 3, 4. There our H is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? If I gave you another molecule, now what is this guy? This is what? Butane, right? What is this? Now, what if I give you another molecule like this? Let's see how many C's this one do we have. How many H's this one we have? 1, 2, 3, 4. How many C's are there first? 4. Let's see how many H's do we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That is also what? C4H10. Is this molecule equal to that molecule? What is the name of this guy? 2-methyl propane. So do you see that they have the same molecular formula now, but differ in their structure? They have different structural formulas, but the same molecular formula. So, and that is concept of isomerism. Now we're going to be going through the types. So this one is an example of the first type. So right, types of isomerism. I mean, now listen. These guys are called isomers of one another. They're called what? Isomers. Let's go. But the phenomenon is isomerism. Joy, move forward a little bit. Move forward a little bit. I want you to be seeing the front door. So I said that the first type, now right, types of isomerism. Number one. No, isomerism is actually grouped into three major types, three broad types. We'll be considering structural isomerism, then we'll also be considering the geometrical isomerism, that is difference in their geometry, geometrical isomerism. Then we also see the conformational isomerism. We've done conformational analysis, haven't we? Conformational analysis. Do you remember? Eclipse, Gauss. But you see, this conformational isomerism is not all the scientists that agree with it, because some scientists think by conformation, because you will see they are basically the same, only their orientation differ. Okay, then geometrical isomerism is just in the rotation of those of units of substituents around a particular molecule. So which family of hydrocarbon will have this, will exhibit this kind of isomerism? And which family? That if you rotate, remember there is a particular one we said, if you rotate the bond, it allows for free rotation, right? And it doesn't alter the molecule, it's still the same. But there's a particular one that once you rotate this thing, because there's no free rotation, once you rotate it, you have changed the molecule entirely. Alkene. The alkenes and in fact, there is no alkyne because there is no angle geometry. This thing is linear now for alkyne. Do you remember? Alkyne is a linear molecule. It's only alkene that forms at 120 degrees. Do you remember? All right. So let's go. So that's just what we have there. Now let's go. The first type of structural isomerism, right? Let's define that. Structural isomerism. Molecules have the same molecular formula, but different structural formula. Basically the same thing as what we defined in isomerism. Now let's do the first type. The first type is straight chain isomerism. Straight chain isomerism. That's the first type of structural isomerism. And that's what we just discussed here. Are you with me? I said structural isomerism is because it's the same as what we did before, what we defined before. Have the same molecular formula, but different structural formula. Is that okay? Now the first type of structural isomerism is what? Straight chain isomerism. I've written that. Now, so in straight chain isomerism, they will differ in the arrangement of a substituent, of a unit around the carbon chain, right? Isomers in straight chain isomerism, right? Isomers differ in the arrangement of a unit or a unit along the carbon to carbon chain. So let's give an example. An example is what we did the other time, but let me give you a different one this time. So the first alkane, for example, that has an isomer is butane. Propane cannot have an isomer because it has 3 carbons. So there's no how you want to rotate. If I remove this carbon, I put it here, I'll still have my longest chain to be 3 carbons. Does that make sense to us? First, let me give an explanation with that butane or pentane. Let's use pentane. Now, we have 5 carbons, right? So we're going to have one, that'll be C5H12. Good. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Do you get it? Now this is pentane. Pentane. Now if I abstracted this guy, this methyl group, and I take it to one, I remove it and put it in another chain. So I will have something like this. I'm saying, so I've removed this guy. I'm going to have how many chains left on the parent chain? 4. 1, 2, 3, 4. Then I just take this guy. Now, when I take this guy, this carbon I'm removing, this methyl group I removed, I cannot put it on the on any terminal carbon again. If I put it on the terminal carbon, what will it give me? Pentane again. God bless you. Do you understand? If I put it on this terminal carbon, because when I say count, I will still have to count with it. So I'll put it on a non-terminal carbon, such as anyone within here. So for example, I could put it here. So I put my methane here now. Methyl here, rather. Then I have the rest here. I have H, 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 H. So now let's count how many carbons does it have? Still 5. So C5. How many H's? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 H's. Do you see that? So, but what's the name of this guy? 3, 2-methyl pentane and what? Butane. Good. I hope you know that if you put it here, it will be the same thing. If you put it here, you'd have to start your counting from there. Do you understand? If you put it, as we put it here now, we start our counting from here. So 1, 2, 2-methyl. Does that make sense? If we have put it here, we still start our counting from here, such that it has the lowest possible number. The next kind of this thing that we can make from this is this. Let's say it was not only this I abstracted. I abstracted the first and the last. So when I abstract it, how many carbons do I have left? 1, 2, 3. Now I decide to put one. Let me put one here. I put my second one here. If I put my other one here, I'll be to see, you know it to still give me this, right? If I put it on terminal carbons, I'll get back one of you isomers I've gotten before. All right. So we have 1, 2, 3. 1, 2, 3. That's 6, 7, 8, 9, 10, 11, 12. Do you see that? How many carbons in total again? C5, H, 12 again. But what is the name of this molecule? 2,2-dimethyl or dimethyl what? Propane. Propane, right? Let's see, let's see the longest possible chain. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. So there's no how we can get 4. Do you get it? So it's 2,2-dimethyl propane. Is that clear? So it brings to us that how many does this guy have now? How many isomers does pentane have? 3. To be itself and 2. Do you understand? You always, to know the number of isomers that you count that guy itself and then the other 2 you can form from it. Now it doesn't mean that, now this thing naturally exists though, they naturally exist on their own. But so by studying their structure, we just notice that they have the same structural form, they have the same molecular form, but different structure. Do you understand? So it's not like, so you should not think that this guy is a derivative of pentane. No. Do you understand? It exists on its own. This guy, 2,2-dimethyl-propane, exists on its own. But we found out that it has the same molecular formula as pentane. Is that okay? So pentane has 3 isomers. Do you understand me? All right. All right. Put that down. So the second one, we called it what? Positional isomerism. Number 2, we said positional isomerism. It's almost the same. Do you get it? It's almost the same. But this time, it is the movement of a substituent along the carbon to carbon chain. What did I say? The movement of a substituent along the carbon to carbon. All right. So, for example, I could have this now. Just the movement of a substance along the carbon to carbon chain. So, I could have this now, for example. What's this? This is what? 2-bromopropane. 2-bromopropane. Now, by the time I move it here, look at this one now. I move it to the first carbon. What does this give me? Bromopropane. Or you say one bromopropane or bromopropane. Is that clear? This positional isomerism. Let's go to number 3. So it's just movement of the substituents around it. That is positional isomerism. The number 3 type is let's put it here. Number 3 type is the functional group isomerism. The functional group isomerism. So molecules with different functional groups have the same structural have the same molecular formula but different structural formula. This is still structure. Molecules with the same with what? Different functional group, yes, have the same molecular formula but different structural formula. Now I'm going to give you an example and see if you already understood what I said about positional and functional group. Some people usually mistake positional isomerism for functional group isomerism. Now look at these two molecules. We have butanol, for example, and give me butanol and no, let's use ethanol, something as simple as that. We have ethanol and we have methoxymethane. Methoxymethane. There's no space between them. Methoxy. All right. So what is the structure? What's the general formula of this? The general formula of alcohol is CnH2n plus 1 OH. This is the general formula. And the general formula of this guy is CnH2n plus 1 O. So for ethanol, F is 2, right? So N is 2. So what we have is C2, H2 brackets 2 plus 1 OH. That becomes C2, H5OH. Alright, structurally we have 1, 2 carbons, 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5 OHs. Let's put 5 H's, right? Then OH will now be attached to one of them. Do you get it? Then let's do this guy. This guy is going to give us methoxymethane. And now, the naming of this one does not conform with the way we name these guys. So let me just draw the structural formula for you, or the condensed formula. This is the condensed formula of methoxymethane. You have CH3OCH3. Methoxymethane. Do you get it? Or methoxymethane rather. So we have CH3, CH3. But my point is this, look at these structures. Are these structures the same? Are they the same? If you want to write the actual molecular formula of this, how many C's do we have? 2. How many H's do we have? 6, right? 5 plus 1. Do you get it? Okay, let me write it down. So C2H6O. Does that make sense? Let's write this. CHO. Do you see that? So what kind of isomerism is this? Functional group isomerism. Tell me what kind of isomerism this is before you write. What kind of isomerism is this? Positional. Positional, because we only moved this OH group around the carbon to carbon chain. Is that clear? So we know the difference now. All right, give me the write the notes fast. Okay, so I said number 4 is what? The chain cycle isomerism. The chain cycle isomerism. An alkane homologue, or a member of the alkane family, that's what I mean. Homologue on the board. An alkane homologue is always an isomer of no. A cycloalkane homologue, I'm sorry. A cyclical alkane, that is cycloalkane. This is where you write it. A cycloalkane. A cycloalkane member or homologue is always an isomer of a corresponding alkene homologue. A corresponding what? Alkene homologue. So I will show you that. The simplest cyclical alkane is what? What's the simplest shape that has boundary? Shape, but what do you call them now? Plane shapes that have borders. What's the simplest? It's a triangle. God bless you. Do you understand? So if I draw a triangle like this, I've told you before in the skeletal structure, these vertices represent carbon. It represents what? So you know this propane. 1, 2, 3. So I could make it into 3 forms. Into cyclical form. 1, 2, 3. Do you get it? Now my triangle is facing down. Anyhow you write it out. Let's see how many carbons will be attached. How many hydrogen rather will be attached? 1, 2. How many does this guy need? 2, 3, 4. This guy 1, 2, 3, 4. Keeping in mind that it's 4 bonds that must be around a carbon, right? 1, 2, 3, 4. All right. So let's see. This is what's the structural and molecular formula of this guy? C 1, 2, 3. How many H's? 1, 2, 3, 4, 5, 6. 6. What family corresponds to this? The alkene. It was the alkene that we said has the general formula CnH2n. H2 double N. So 3 double 3, that's 6, right? So if I give you C3, you give me this. I give you H. How many H's would you have? 2 into bracket 3. That's what? 6. So let's draw that in alkene family. Alkene families are the ones that have how many bonds? Double bonds. So we have C. I decide to put it on the first carbon, 1, 2, then, and the remaining 2 carbons. So when we want to, let's add our hydrogens. Let's add our hydrogens. We have 1, 2. Okay. How many would this guy need more? 2. So we'll put them at an angle like this. So this guy, 1, because that's 1, 2, 3, 4. Does that make sense? Then this guy will have 1, 2, 3. Is that clear? Keeping in mind that 4 bonds must be around carbon. 4 bonds must be around this carbon. 4 bonds around this carbon. Is that okay? So let's count how many carbons we have. C3 is still here. Let's see how many H's. 1, 2, 3, 4, 5, 6, 8. Do you get it? So a particular alkene will have the same molecular formula as a corresponding cycloalkane. Does that make sense? So if I say hexene, what will be the corresponding, what will be the isomer of hexene? Cyclohexane. Let's prove that. 6, right? So we'll just draw a 6 carbon ring. 1, 2, 3, 4, 5, 6. So I mean, you know, 4 carbons, 1, 2, 4 bonds, 1, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So by the time you count all of these, you're going to have 6 carbons and 12, because this one carries 12 hydrogens. And that's just the general formula of the molecular formula of hexene too. Hexene is C double bond, 1, 2, 3, 4, 5, 6. So here, I'm going to have this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Do you see that? Does it work? All right, let's go. Number 5. Copy that. Right? Metamerism. You get it? Now, meta is from the word meta, and it means, it's a Greek word, I forgot it. It means metaphysics. That's what. Ah, do you know it? Meta. Eh? Do you know it? The word meta. Okay. Metamerism. Give me. Metamerism. Um, is a type of isomerism that occurs when there is an heteroatom in the molecule. There's what? An heteroatom in the molecule. Heteroatom in the molecule. So heteroatom. Okay. I think we misplaced it. Functional group isomerism, where we did oxy, methoxy, and all the other time. Alkoxyl group and alcohol the other time. That would be metamerism. Because the example coming to my head now is this. There is also a type of isomerism between, you know, aldehydes, right? Alkanals, right? And alkanones. Alkanones. Are they isomers? No, they're not isomers. They're not isomers because this one has a terminal carbon. This one doesn't have the functional group is not The functional group is terminal here. Here, the functional group is not terminal. So if the functional group is not terminal, it means to still have a hydrogen more than this. Does that make sense? Still have a hydrogen more than this. So alkanal is going to have. Okay, let's do this. Let's give, for example, butanone. Let's see what butanone is. Butanone is this. 1, 2, 3, 4 carbons. On because it has the carboxyl. You know that the functional group of these two is called carbonyl. It's called what? Carbonyl. And what's carbonyl? R C double bond O. C double bond O. This is what we call carbonyl. Do you get it? So I can put my C double bond O here. Then here I have 1, 2, 3. Here 1, 2, 1, 2, 1, 2. Okay, let's see what happens here. Now, how many C's do we have here? 4. C4, H, 1, 2, 3, 4, 5, 6, 7, 8. H8. It's going to correspond to what? Let's see butanol. Let's see the formula for butanol. Butanol. The carbonyl group will be terminal. So we're going to have 1, 2, 3, 4. Are you with me? So if the carbonyl group is terminal, we're going to have, maybe we're going to have this. We're going to have 1, 2, 1, 2, 1, 2. 1, 1, 2, 3, 4, 5, 6, 7, 8. Then they are isomers. Do you get it? Butanone and butanol, they are isomers. Because seeing this, we have what? C4, H, how many H's? 1, 2, 3, 4, 5, 6, 7, 8. And O here, right? O and O. So aldehydes, these guys are called aldehydes. They are called what? And these guys are called ketones. Somebody say ketones. So these guys are carbohydrates, basically. They're what? We call these ones simple sugars. We call this one reducing sugar. Say reducing sugar. Reducing sugar. All right. Put that down. So we have butanol. So propanol is going to have this. It's going to be an isomer of propanone. Draw it down. That should be. I'm going to clean this. Yeah, for metamerism. God bless you. That'll be your example. So we didn't screw it up. We didn't screw it up. Do you understand? We didn't screw it. We had the same. No. We still messed it up. So that one, this one is functional group isomerism. That one is what? Metamerism. You know, we mentioned that, okay, I didn't tell you the meaning of heteroatom. We said when a group is attached to what? An heteroatom, right? Example is OSN. Those are the major three that we use. Or NOS. Okay, NOS. Those are the major three we use. Nitrogen, oxygen. So for example, in a mine group, you see metamerism occur. In alkoxyl groups, you see metamerism occur. Does that make sense now? And the one that have sulfur too, metamerism will also occur. Do you get it now? All right. So this one will be functional group, different functional group. This functional group here is called, they are both carbonyl functional group, but one is terminal, the other is within the chain. Do you get it? So we call this one R, we call this one on. Does that make sense? All right, put that down. So you give me your own example using propanol and propanone. I'm cleaning my own. See you tomorrow. All right, let's go to the next one, which I'll consider the last one. Tautomerism. Now this one is almost the same guy. Okay, this is it. So it exists when there is a dynamic equilibrium. When there's what? When there's a dynamic equilibrium between two forms of a molecule or two forms of a compound. It exists when there exists This is a phenomenon that exists when there is dynamic equilibrium. Dynamic, for those that cannot spell it. Dynamic equilibrium. What do you have to check the board? You can spell it. You see, you don't look, and you still looked at it. You still looked at it. Okay. So dynamic equilibrium between who and who? Two forms of a compound. So it's the same compound, but it exists in two possible forms. So when it changes form, it's going to enter another group. You understand now? Let me give you something. Let me give you one. Look at this. Give me this guy. Listen. Please come. Do you want to see me? Do you want to see me, sir? When there is, so there's dynamic equilibrium between two forms of a particular compound. So for example, I give you, let's use propanone, the same propanone. CCC. I can see a bird. CCC. Now what? This propanone, right? Double bond O. What's this O? What's this O? So now, it is possible that, now this is what tautomerism is. This is what tautomerism is. There are two bonds here, right? One is, the other is it clear? Nobody is confused, right? Good. So these pi bonds contain pi electrons, right? I mean, one from what we did in hybridization. One from one guy, one from the other guy. They will laterally overlap, right? So there are two electrons here too, right? So it is possible that sometimes in the presence of a reagent, but the condition is just that these two electrons will be abstracted by this guy. Do you understand? So when this guy takes it up, it will become, the intermediate form will become something like this. And then there will be two electrons there. Do you understand? Then now use the two electrons to form a bond with another compound. Is that okay? It will abstract these two electrons, these two pi electrons, and become this. So to have a negative formal charge. Is that okay? And so now use those electrons to react with maybe an H, for example. So if it reacts with an H, this is what will happen. This guy needs how many bonds between around it? 4, right? So one of these electrons will come down and form a bond here, a double bond. So let me draw you. So this is the intermediate molecule. So the final molecule will now become this intermediate. The final molecule will now become something like this. OH. Is that okay? Then CH. And there will be a double bond there. Okay, yeah. Now if there's a double bond there, it means that this H will leave. Does that make sense? Then you have this. So this guy, so let's name the guy that we started with. We started with propanone. See, it makes sense. Prop 3. R because of single bond. Non because of carbonyl. Does that make sense? Does that make sense? Then here we have what? Still prop, but now pen null. Do you get it? Who is confused? Don't lie. Listen. All right. So what did we start with? We started with propanone and ended with what? Propanol, not propanol. Propan, N. N for what? Double bond. Do you understand? The N is for what? Double bond. Then all for what? OH. Is that okay? All right. Let's put that down. And now the N for isomerism. All right. So those 6 that we considered are the types of structural isomerism. And they are what? Chain, straight chain cycle, positional, functional group, metamerism, and tautomerism. Is that okay? So I did mention the fact that those guys, for the ones that we did metamerism on, each of those molecules will be called metamers. They will be called what? And the one that we did tautomerism on. Each molecule will be called what? Tautomers. All right. So let's go to geometrical isomerism. This is a phenomenon, or this is a type of isomerism in which, this is a type of isomerism in which two organic compounds have the same molecular formula but different orientation in space. They have different what? Yes. They have the same molecular formula but different orientation in space. This type of isomerism is seen in molecules that have double bonds or triple bonds. That have double bonds or triple bonds, which, as we recall, do not allow for free rotation about, just say which, you don't have to who as we recall. I'm just saying that you recall. Do you understand? But if you have written, there's no problem. Which, as we recall, do not allow for free rotation about the carbon to carbon molecule, double bond. No. You're writing carbon to carbon double bond. Carbon to carbon double bond, that's what I mean. Do you get now? Which, as we recall, do not allow for free rotation about the C double bond C. Do you understand now? So when you have a molecule like this, that's when you can have geometric isomerism. Now there are two types of geometric isomerism. We have the cis. Okay. The name is not even geometric isomerism. The name is stereoisomerism. Do you understand? So stereoisomerism is split into two: geometrical and optical. Is that okay? Optical isomerism. So with optical isomerism, we have to learn what is called chirality. So now let's go. So, geometric isomerism. There are two forms. Consider an ethene molecule. Consider an ethene molecule. Consider an ethene molecule. A double substituted ethene molecule. So look at ethene now. I substitute twice. Say with the same substituent. Is that okay? I'm substituting with the same substituent. So let me use chlorine. If the chlorine appear on the same side like this, there is a name for it. So this thing, you know that this is C. If I wanted to write this, I would write CH. How would I write this? CH2Cl, right? And CH2Cl. Isn't it? This is the condensed form, right? Is this one clear? No. CHCl now. Do you get it? That one I wrote was ethane, chloroethane, dichloroethane, 1,2-dichloroethane. So this is CHCl. Does this make sense? Is it clear? Now, you see that this guy, if I change this molecule to this, C double bond C, put Cl here, put H here, put H here, and put Cl here. If I change the molecule like this, this thing I have is still CHCl and CHCl. Cl. Does this make sense? So what's the difference between them? The difference is that I have said that this, so this carbon is, what's the hybridization of this carbon? sp2 hybridized. What's the hybridization of this carbon compound? sp2 compound, every sp2 carbon. So they are both sp2s, meaning that there is a double bond attached somewhere. So, and that is in the middle of both of them. Now, this double bond, we said, does not allow for free rotation because of what is called torsional strain. You know what is called what? Think of it as strain. Torsional strain occurs when you want to change the molecule, turn it around. So let's say I want to, if it were this, see, watch, you get this now, you understand it very well. Watch this. Let me put this on it, Cl and H. If I change this molecule, I turn it. I did not, nothing about this molecule would change. Nothing about it. But scientists found out that the moment you turn this molecule around, it changed the boiling property of these guys. One has, I think the trans form has a lower boiling point than the cis form. Now we'll name it. You understand what I mean by cis and trans form. So the two forms of geometrical isomers are the cis form and the trans form. So cis is a Latin word for same. Cis is a Latin word for what? Well, was it in your class I was talking about cisgender that I was talking about? Yes, So cisgender means the same gender. Is that okay? And transgender means what? Someone that switched gender. So imagine as I'm a man now. I also say, I want to become a woman. I will go and add bubbles here. I'll go and add plastic Botox. Then I'll now, what again? If I don't have this, right? My Adam's apple is not apparent, is it? It's not apparent. So I don't know. I'll be wearing turtleneck every day. Then I'll shave my beard. There's one cream I heard even disappears your beard. Now like, it's not going again. What is it? Vet. No, that one is for shaving. That one is for removing by yourself. There's one that if you put it like this, it's not going again. So I'll use that. Then I'll wear wig. And I go like this. Then I ask you. Then I come. Isomerism is different. Anytime I want to stand, I must stand on one leg. So that's transgender. But it's not fitting. Will it fit me? God will bless you in the name of Jesus. How can that kind of thing fit me? So we have trans. Trans means switching from one to the other, right? So what does that mean? Trans means different. Think of it like that way. Different. So look, this is what confuses students. They usually see molecules like this. So someone will ask something like, what if I had something like this? Cl here, Cl here. Everyone see. Have you thought of this before? That with this, how would you name this? Okay, so wait. When the molecules, stop writing, I want you to get this. When the molecules you want to name, when the molecules, the substituents that are attached are on the same side. How are they on the same side? They are on the same side of the bond, not of the carbon. So there are two sides of the bond. I mean, if you are rotating like this. So there's one side there's one side of the board on top. There's one side, I've marked a bit so that I don't say sorry. I heard the people that say sorry. Okay, so there's one side up here and there's another side down here. If they are on the same side, we call it cis. Call it what? Cis. So to name this guy, I will say cis. How many chlorine do I have? 2, right? 2 cis 1, 2 dichloroethene. Does that make sense? So cis because this is also 1, 2 dichloroethene, if you like it or not. But they're on different sides. So this one will be called trans 1, 2 dichloroethene. Does that make sense? But look at this guy. This is not a geometry. This one does not exhibit geometric isomer. Now, because you might be thinking it's on the same side. They are not. This is not the same side because the same side is viewed with respect to the bond. There are two parts to the bond. See, there's a side here and there's a side here. Do you understand? So if it's on the positive side, both of them are on the same side. So if one is on the positive side, the other is on the negative side, both of them are on different sides. So these two could also be here. So I could twist this molecule like this, but I will not cause torsional strain here. Because what I've done is like I capsize it. See, this is different. For example, so see the double bond here. I cannot rotate this carbon like this. If I rotate it, Holy Spirit, I bless God. Now see this. This guy is the double bond. Does that make sense? This is the double bond. Now, if these two heads are the substituents, chlorine, chlorine. If they are on the same side, this is cis whatever the name. So 1,2-dichloroethene. Ethene because it's double bond. It doesn't exist with single bond, I repeat. Is that okay? But if I twisted this around this double bond, there will be torsional strain within this molecule. And that torsional strain might result in a higher boiling point for this guy. Or maybe a less boiling point. I can't even remember which one now. Is that okay? But the basic thing is that they will be different in the chemical property. Do you understand now? So this guy has a... So this guy, you're going to say that the chlorine is on this side and the chlorine is on this side. Do you understand? So this thing is different from when I wear this cap on this one. They are different. Do you get it? And also, if I decide to move this, they were like this. If I decide to move the entire bond like this, it's still cis. You know, the whole bond moved. There's no torsional strain. It's as if it's a belt. It's like a belt. So good. So look at this my bag now. If I decide to twist this thing around it, there'll be torsional strain on the bond. Does that make sense now? All right, so that's what we mean. That's what we mean. We're done. Where did I get this from? Okay. All right. Let's go to the next one. So that's cis-trans isomerism. Did we all get it? All right. It happens around only the double bond though, because they might give you larger molecules. For example, I could put C2H5 here and put CH3 here. This is also transform. But the way you name it is you still follow the rule. 1, 2, 3, 4, 5. Pent. But you put trans to show that they are what? On different sides. Is that okay? All right. Good. Let's go to... Wait, look here. I know it will confuse you because the larger the molecule sometimes, the more confusing it might be. So look at this guy and look at this guy. You should only write now if you understand it. If you don't understand it, please listen. Look at this guy. To name this guy now, CH3, sorry, CH3. So to name this guy, you count 1, 2, 3, 4. Is that okay? 4, 5, 4, 5. So that will be pent, right? No substituent attached, right? So this will become what? Because these molecules are on the same side of the double bond, we say this is cis what? Pent 1, 2, carbon 2, 2 in, pent 2 in. Does that make sense? Because the double bond, this in is on double, is on carbon 2. Is it clear? Cis pent 2 in. But this guy, they're on different sides. We say trans pent 2 in. It's pent 2 in, pent 2 in. But trans form, cis form. Exactly. So that's it. Right, let's go to the next one. Optical isomerism. This exists when a molecule has a chiral carbon. Have you written it? Let's pause it. Are we there? So I said that, look at this guy. Chirality is when a carbon atom is a, let's all eyes be on the board now. A carbon atom is attached to 4 different groups. So this guy is attached to, what group is this? Amine. What group is this? Carboxylic acid. What group is this? Alkyl, but this time methyl, right? What group is this? Also alkyl, right? But there are 2 different types of alkyl here, right? So you see that there are different groups that are surrounding this molecule, this carbon, eh? So this carbon here is a chiral carbon. Is what? So I could have a molecule like this. Watch me, for example. I have a molecule like this. CCC, like this. Is there a chiral carbon there? So let's ask. Let's check together. Is this carbon chiral? Is this carbon chiral? Is this carbon chiral? Good. How is it chiral? It's attached to ethyl, methyl, oxyl, and oil, and chloro. So this is what? Chiral. So for these 2, because they are chiral, this carbon is chiral, this carbon is chiral, this molecule will exhibit optical isomerism. Is that okay? Let's check one more molecule before. No, they are not isomers, they are not isomers. I will show you the isomers. These are not that this guy will have an optical isomer, that's what I mean. This guy too will have an optical isomers, but they are not isomers, so I'm just giving you examples. These are the examples you are likely to see. But I use this one so that you see it's vivid. It's very clear that it's different, right? All right, let's see this. Now, is there a chiral carbon here? Sorry. Is there a chiral carbon here? What's the chiral carbon? Carbon, is it carbon 1? The 3rd carbon is chiral. Okay, let's analyze. Who agrees also chiral? You don't agree, Tolu? Is it chiral? Is it chiral, Esther? It's chiral. So is it chiral? Okay, let's see. So we have a different group: bromo, chloro, C2H5, ethyl, C2H5. So it's non-chiral. Do you get it? It's non-chiral. What if I were to put OH here? Will it be chiral? It will be chiral. That OH group is added to this guy. Is it this one that will be chiral or this one that will be chiral? Eh? None of them will be chiral. Okay, let's check. As far as we know that it will be 4 different groups, let me redraw it so that it will be neater. I have C1, 2, 3, C1, 2, C, BR, CL, COH, CH, CH3. Alright, let's see this together. So let's go. The first carbon, chiral or achiral, that's another word for it. If it's not chiral, you say what? Achiral. So chiral or achiral, it's not achiral. Chiral, I know I would have common sense here. Chiral or achiral, chiral or achiral, chiral or achiral. Okay. Is he ever like see achiral for this guy? If you have for achiral, this guy achiral, raise your hand. This 3rd carbon, achiral. Akara. Who else is Akara? Okay, we have Kara. Kara for this guy. Raise your hand. Kara for this third carbon. Kara, 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 Kara. Which one are you? You are not Kara. You are not Akara. What do you want to be? You want to be Kara. All right. Now let's see. How about this carbon? We have for Akara for this carbon. Raise your hand. Akara, not Kara. Akara only have. So the rest of us Kara. Fourth carbon there in this direction. Akara or Akaira. 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 Sai. Akaira. Who else? Okay, so it means the rest of us, Kyra, for this guy. Who said no? And so what are you now? You must be one of the two. You can't sit on the fence. There's no fence, they will break it. Okay, let's do it together. Let's do it together. Let's see. What is the definition of chirality? A carbon, we have what? 4 different groups surrounding. Let's go. So this guy, does he have 4 different groups? No. HH? No. HH? No. Now let's go to this guy. Now there is Cl, there is Br, there is C2H5, or you say there is CH2 and CH3, right? On this guy, there is CHOH and there is CH3 attached to it. Are these groups the same? Are these groups the same? Chiral. Let's go on. This guy, there is, on this side we have CH3. On the bottom we have H. At the top we have OH. On this side we have some different nonsense, right? R and X and all. Are they the same? Chiral. So both of them are chiral. Chiral. Do we understand? You see, it's very simple, right? Chirality and achirality are simple. Now, so if these guys exhibit chirality, they have chiral carbon at all, they will exhibit optical isomerism, right? In optical isomerism is the ability of a molecule No. This is the ability. Oh, yeah. No. How do I put this? Optical isomerism is the okay. We've said it exists in different forms, right? What did you say? We said this exists when a okay, yes, good. It's the ability of a molecule with a chiral carbon to rotate plane polarized light. To rotate what? Plane polarized light. Plane polarized. In ways we've talked about polarization of light before, right? Making lights that is transverse to pass to become what? To go in one direction as plane polarization. It's simple, just so to rotate plane polarized light. So a molecule will rotate plane polarized light. By polarizing the lights, full stop, by polarizing the lights, it results in two optical structures that are non-superimposable mirror images of each other. What did we say? Two optical structures, by polarizing the light, it results in two optical structures that are what? Non-superimposable mirror images of each other. Now, we'll explain. So we said the plane polarized light will give rise to what? non-superimposable mirror images. Is that okay? All right. So in one, the main functional group will be rotated to the right, or the heavy molecule will be rotated to the right. This is called the d-isomer. In one, we said two non-superimposable mirror images, right? So one is the molecule itself. The second one is what? Is the one you are seeing in the mirror. Are you with me? So I now said that, what happened? Yes, in one, the heavy molecule will be rotated to the right, which is called the d-isomer. Or we call it the dextrorotatory structure. D-isomer what? Dextrorotatory structure. And in the other, the main functional group or the heavy molecule will be rotated to the left. And that one will be called the L-isomer or the livo-rotatory structure. Does that make sense? The other one will be, and in the other one, the main functional group or the what? The main functional group or the heaviest molecule will be rotated to the left. And that will be called what? L-isomer or livo-rotatory structure. So this is how to prove this at home. In your house, when you draw a structure like this, you come and use a mirror. So for example, if you want to view with me now, you can come and see. You see that for me, the mirror, this thing will, you want to come and check? Why is it not turning it? It's actually supposed to turn it. Like lateral inversion. Do you remember lateral inversion? But it's not going to happen like lateral inversion, because lateral inversion is just the letter that changed. Is that okay? But what should happen is that the mirror, if you check this in a mirror, where will you see this? We know mirror laterally inverts, right? I'm going to do it in mirror now. So if you were checking this, viewing this from a mirror, where would you see this COH? On this side. Do you understand? Or where will you see this guy? On this side. Do you have a mirror? Where is it? At home. No, don't worry, don't worry. But that's the way to be. When I'm going to test it at home, you don't have to. If you see yourself in the mirror, if you raise your right hand, what do you see? So okay, so you don't know. Well, okay, so if you raise your hand in the mirror, do you see the person raising hand on this side? What do you see? Somebody facing you raising up hand like this, right? Do you understand? It's still right, but now in your left side. Do you understand now? Who is confused? So we call them mirror images. We call them what? They are non-superimposable. They are what? What is superimposition? Now, these hands are mirror images of each other. If you have your hand to be longer than the other, raise your hand. Let's see abnormal people here. Okay, no, your palms. If you have your own palm, one is longer than the other, that they are not equal. Just go, man. Okay, nobody, right? And yeah, go. You're already tired. Okay, are we here? Okay, you don't even have two fingers. All right, look here. Now, these two palms, are you with me? These two palms are mirror images because they are non-superimposable. This is not superimposition. Superimposition means lay them on each other. If you lay them on each other, do you get the same thing? No. So they are non-superimposable. So that's the same kind of thing that we form with what? Optical isomers. The one that is rotated to the right will be called what? D-isomer. Left. L-isomer. Just remember L for left. So if L is for left, then the other isomer will be what? So if you have heard glucose D, have you heard glucose D before? So that's the D-isomer of what? Glucose is the most abundant, it's the most common, it's the most stable form of glucose. Yes, there's glucosale, where the terminal OH group. So glucose will be around like this. I hope I still remember that shape. 1, 2, 3, 4, 5, 6, right? H2OH. So here we have OH here, OH here, H, H. So 1, 2, 3, 4, 5. Let's draw the sixth one. Now here, the OH is here. What direction is this? Left, right? This is called this terminal carbon is what we used to name them. You understand? The second to the last OH group. The carbon attached to the second to the last OH group is the carbon we used to name them. Is that okay? This thing, when I teach you carbohydrates, I'm going to teach you how to draw this. So is that okay? This one is called the Haworth convention. It's called what? Because we'll be drawing Newman projection. No, this is called the Newman projection. Share conformation. And so that one is Haworth. This one is Haworth. I think this is Haworth. This is Haworth. Then this one is Newman. You would have seen this in your textbook before. Something like this. Do you remember? You remember seeing something like this, right? You don't remember? Okay, it's simple to draw. Don't worry. I'll teach you how to draw it. Which one? And yes. As in based on conformation. This one is on conformation. Do you get it? So this cyclical form is the same thing. It's formed when the OH here attacks, or the OH here rather, this OH here. There's just an attack between this fifth carbon and one of this. I think this OH here attacks the OH here, or one of these, that thing. I'll teach you when we get there. But the point is this. The point is that 1, 2, 3, 4, 5, 6. That's C6H12O6 that you see. C6H12O6. This here. Is that okay? C6, 1, 2, 3, 4, 5, 6. H12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. How is that? Okay, C double bond. Oh, I'm sorry. So yes, double bond. Oh. Is it at the last one here? OH is here for this carbon. So this is it. Yes, this is it. Do you get it? Is it different? What is it supposed to be? This is it now. So this guy, so let's count again. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. H12, O6, 1, 2, 3, 4, 5, 6. Do you get it? So that's glucose D. And this is glucose L because the OH is going to be on the. In fact, this is glucose D, this is not glucose L. Do you know why? OH is on which side here? This last OH, terminal OH, is on left. But when you put a mirror here, what does it do? Turn to the right. So that is what glucose is this? Glucose D. Do you understand now? Is it clear? Who is confused? So with each of these cases, they also rotate plane polarized lights that way. Do you understand? And they will form D and L isomers. D and L isomers. Alright. So that will be that for isomerism. Do well to subscribe to the channel. And that's it.